When a process is executing, it's actually executing certain subset of the commands in the code. If there are conditions in the code, such as if else or case condition, or a loop that has variable length, then the outcomes of execution of a certain process changes according to which path of the execution the process will take. This certain order we can call a thread of execution, as if these commands are linked with a thread. Usually, when you think of a process, you think of a single thread of execution, but that's not always the case. Actually, on contrary, a single process might be able to execute multiple threads of execution at the same time. And we can take a web browser as a very good example. A web browser will be displaying text, maybe video. It might also play music while it's downloading something else. All these are actually parts of the code of the web browser, and it's running at the same time. So there are several threads of execution at this case. If you have multiple threads of execution, you have to be able to represent this, to show it in your process control block. Threads will be a whole chapter to discuss all the concepts in multi-threading and how it's actually applied by operating systems. Processes in the operating system are actually represented by their process control block. And pointers to the process control block will be created according to the state of the process. If the process is ready, a pointer that links this process to the ready queue, that's to say the queue of the ready processes that are waiting for the CPU, will be created. If the process is waiting for an input from a certain input device, so it will be to indicate that this process is waiting for this device, a pointer that link this process to the other processes waiting for the device will be created, and so forth. In Linux, for example, processes are represented with a double linked list of their process control blocks. As I've just mentioned, processes might be waiting for the CPU or might be waiting for input-output devices. So who gets the turn in the CPU? This is a job for a system program that we call the scheduler. Schedulers are the program that make decision in regard of changing the state of the process. Process schedulers are mainly two schedulers, long-term scheduler and short-term scheduler. And they are governing multiple queues in the operating system. Job queue and this contains all the processes in the system in all their states. Ready queue, and this holds the ready processes that are waiting for the CPU to be executed. Device queues, and these hold the processes that are waiting for input or output operations. And processes apparently migrate from one queue to another queue. If you want to have this abstract look of the operating system and how processes migrate from one queue to another queue, first we will have the ready queue as a double linked list where all the processes that are ready will be linked by pointers in this queue. Every device has its queue, and if there is any process waiting to use that device, a pointer will be created, linking this process in a double linked list. How the migration happens. A process, a new process, after being granted all the resources it needs to run, will be admitted into the ready queue. When it has its turn to use the CPU, it will go into the CPU and start its execution. If it's finished execution, then it will terminate and it will exit the system. Otherwise, it's either waiting for an input-output request, so it will go and join an input-output queue, or the time slice that is what it was given to this process has expired, has finished. So it will again go and join the ready queue because it's ready. It's waiting for nothing. Or this process actually created another process to do a task for it. For example, you are using a word process and you decided to save your work. You will notice that the software will actually have this small pause, almost unnoticed. In this small pause, the software will create another process that will save the document to the storage device and return the control to the original process. Or maybe this process is waiting for an interruption, a signal, if it's a timed process, for example. So it will be waiting for the interrupt. If the process has created a child, forked a child, then the process will wait until the child finishes execution and return the control to the parent. If the process is waiting for a signal, it won't be executing again until this signal is sent to the process. In either cases, the completion of input-output request, the child finishes execution, or the interrupt occurs, then the process will be ready again. It will join the ready queue.